Hello and welcome to the next video in chapter 34 from the book by Nate. In this video we're going to go over lenses. So the first half we're going to go over ray tracing and how to show graphically what happens when light passes through a lens. And then the second half of the video we'll get to more quantitative aspects of the same phenomena. So in particular we really want to be able to get to the lens equation and know how to use the lens equation in figuring out the location and properties of images formed by lenses. Okay, so our problem today is it's qualitative. It has to do with this particular ray diagram. So we're going to learn some rules for drawing these sort of diagrams. But given that a light ray does this after it passes through something, we can say some information about the lens and what kind of image is produced. So we'll get back to this. Okay, so there's two types of lenses, converging or diverging. Converging and diverging. And we have a different symbol for each of these two things. And the symbol matches exactly what the lens looks like if you were to make this lens. So also later on in this video we're going to go over something called the lens maker's equation, which tells you, based on some geometrical properties of your lens, what will it do to light. So a converging lens looks something like this in general. So suppose this material is made of glass, and a lot of times we won't draw anything in the middle there. We'll just draw the boundary. So a converging lens has it's thicker in the center than at the edges. So this is one very easy way to see, because you can also actually have a converging lens that looks like this. And we'll talk about that later in the video. So as long as, so the canonical way of showing it is this one in the center. So I'm going to delete this other one. We'll get to types of lenses in just a second. This other one is called a meniscus. But notice how it's still thicker at the center than at the edges. So this is a converging lens, this is a converging lens. Or if you had this side flat, that's also a converging lens. As long as the glass is thicker at the center than at the edges, then it's converging. So diverging, you could probably guess, is thinner at the center than at the edges. Okay. So this is the way we draw these. And then there's a central axis for both of these. So we call this the principal axis, or axis of symmetry. The gist of the difference between these two is that if you had light coming in parallel, these lenses do different things to these light rays. So a converging lens will take these parallel rays and they'll focus them. They'll bend the light towards the symmetry axis. And they actually bend the light rays towards the same point. So the one in the center just keeps going. This one will be bent this way, and this one will be bent this way. All towards that same point. So this is called the focal point. So a converging lens will bend the light straight towards that point. A diverging lens will take these parallel light rays and they'll bend them away. So notice, so as soon as I draw that first one, I'm going to just note this point right here, so that this light ray was bent away, and then if I trace it back, it goes to this point. So all of these light rays actually, if I trace it back, it'll be traced back to the same point. So I'm going to try and draw this. So all of these rays have the property that if I trace them back, they're all traced back to that same point. So even though the light rays aren't being focused right here, this point is still called, even for a diverging lens, we have the focal point right here. Okay. So this distance is unique for each lens. So the distance that the lens is away from that point is called the focal length. So this distance has magnitude f in both of these cases. But for a converging lens, we also have the convention that this f value has sign positive, has positive sign. So if your lens is converging, it has some amount that, so the distance from the center of the lens to where the light rays will converge right here is the magnitude of f, and we force it to be positive for a converging lens. For a diverging lens, that distance also has magnitude f, what we call f, except to denote that it's a diverging lens, we make it negative. Okay, so there's a lot of information contained in that, in the focal length. And we're a little sloppy with language. We say focal length even if it's negative. We'll say the focal length, we might say the focal length is -5 centimeters. So obviously that's not just a length, but there's some information contained in there. Okay, so the reason these lenses act like this is really there's Snell's law going on at each of these two interfaces. So really if we zoomed in right here, we would have to do Snell's law at this interface and Snell's law at this interface and then continue the light rays. So these light rays will meet all at one point, or look like they diverged all at one point, as long as this is a thin lens. As long as this doesn't, the thickness here is small compared to that focal length. So that's why, so notice how the section title is called thin lenses. It's the focal point is only uniquely defined for spherical shapes right here, in the case that the lenses are thin. So we're only going to deal with thin lenses. We're not going to try and get corrections to this factor. We're just going to deal with this case in these sections. Okay. So there are some rules that you need to know for drawing these ray diagrams. So what we just drew right here is a special case where the incoming light rays were parallel. We're all parallel to one another. So that happens if your object was very, very, very far away. So if I had a person very, very far away, the light rays took a long time to get here and they come in approximately parallel. But we're going to want to draw general pictures. So I'm going to call this general ray tracing. So let's suppose we had a converging lens. This is our axis of symmetry. And so what we do here is we symbolize the object with an arrow. So it'll make maybe a little bit more sense after we see the image here, but we're gonna focus on all the light rays that start at the tip of the arrow right here. Okay, so I'm gonna give you some rules for some of the main, what are called principal rays. So I think draw the 3 special rays from the tip of the arrow. So principal rays, special rays. So one of them, so principal, we'll keep a list as we draw them. Principal rays, or what your book calls special rays. If you're using another textbook, principal is also how they describe it. So one of them is that a parallel light ray bends towards the focus. Okay, so what that means on this diagram is we have a parallel light ray, and let's suppose the focus is about right here. So you'll see why I drew one on both sides in just a second. So notice how this one, it looks like that there's only a focal point on the right for a converging lens. But actually it's useful to have both of these. So you'll see in just a second why this is. So this light ray that I just drew, it's going to bend towards this focal point. Okay, so this is the light ray. So you could draw arrows, but you don't. Maybe it'll clutter up the diagram, so I might get rid of them in just a second. Okay, so that was one of the principal rays. Parallel ray bends towards the focus. So by parallel, I mean parallel to the symmetry axis. Okay, another ray is that rays through the center of the lens are unaffected. Through center are unaffected. Okay, so this light ray right here is not going to do anything. It's just going to keep going. So you can start to see actually, and actually it just takes two lines to meet at a point, right? So actually, we can start to see where these light rays might converge here. So notice how, okay, so let me talk about the third one in another color, because otherwise the diagram's going to get a little messy here. 3. And really this is like number 1. So number 3 and number 1 are very, very similar. You have to imagine that on the other side, we could have had a light ray go through here and then go through this lens and then bend towards the normal, like this, right? So we want to choose a light ray that's going to emerge parallel. So the one that does that is actually the one that's going to pass through the focus on this side. And if I drew this accurately enough, and notice how the lens doesn't actually extend all this way. So we're imagining that all the light is going to go through the lens. But in this diagram, you know, I happen to not draw the lens, you know, long enough. So the convention is that you just imagine that the lens is long enough that this light ray did actually go through the lens. So this one emerges parallel. And they should have all crossed. You know, maybe if I used a ruler, this would have been a little bit better. They should have all crossed at the same point. I think you can kind of see that this one, I started to slope it downwards. So this is why you want to draw more than 2, because it helps you correct for any mistakes you might be making. That one maybe is a little better. I don't know. So this is where they all meet. So I'm going to start drawing this in another color. So I guess I should first comment. So a ray through the near focus emerges parallel. Okay, so this is just like number 1, but viewed from the other side, right? So it's parallel and then goes through the focus. Okay, so what do we do with this ray diagram? So here all of our light rays, all of our solid lines meet up at this point. So this was the tip of the arrow. We could actually have done this for any part of the arrow, and we would get that they all meet up at points along here. And so actually what happens is that we have an image where the arrow is inverted. See how the tip of the arrow actually appears on the other side now. So this was our object. This is our image. So the location where all those light rays meet is where you have the image. So in other words, what this means is that if I look at the light rays that have passed through my lens, it looks like there's an object right here. Okay, and there's a few qualifiers here, or a few adjectives. So for this example, we can actually say a few things. So first of all, it's a real image. So we're going to talk about real versus virtual images. This is a real image because light rays actually cross at that point. So I'll do another example in a few minutes with a diverging lens where we actually get a virtual image. So light rays actually cross here, so it's real. This one's enlarged because the arrow is bigger. So in other words, if you looked at light that passed through the lens, you would actually see whatever this object was. And we use an arrow just for consistency, but really this object could be anything. It could be a little turtle toy action figure, a Teenage Mutant Ninja Turtle. So you would see like a hologram of the turtle that's even bigger, and you would see it in front of the lens. So it would look a little backwards. So you stand your turtle upright, it's going to be upside down, but it's going to be a hologram where it's upside down and it looks bigger. Real, enlarged, and this one is inverted image. So we'll see if it's not real, it's virtual. If it's not enlarged, it's reduced, or maybe it's the same size. and then if it's not inverted, it's upright. So we'll see an example where it's the opposite of all these in just a second. Okay, so this is one example. And you want to keep in mind these principal rays. Okay, so you want to get some practice drawing these. And in general, it's nice to have a straight edge or a ruler for you to have handy. Okay, so let's look at another example of this. So we'll talk about magnification in just a second. So this is an equation. I want to wait until we get to the quantitative part to look at this. Okay. All right, another example. So this time let's have a diverging lens. So we have a diverging lens. We're going to draw our symmetry axis, and we're going to have our object right here. Okay. And let's say that the focal point is right here. So there's a near focal point and a far focal point. Okay, let's draw some of these. So there's the parallel light ray. Now this one, because we have a diverging lens, and again, even though it looks like it's outside the lens, we're going to imagine this light ray went through the lens. So because we have a diverging lens, this is going to bend away from our focal point, and we have to trace it back. So it looks like it came. So this light ray looks like it came from that point, from that near focal point. And then there's the so another one that we could draw is the light ray that goes through the center of the lens, and that just passes through unaffected. So if I could draw this, there we go, a little better. That's a little straighter. So that passes through the center right there. And then there's another light ray that, so there's a light ray that actually, so I'm going to draw the light ray that's, so I'm going to use a different color just to emphasize, just so that the picture doesn't get too cluttered. But I'm trying to draw the light ray that would go towards this focal point right here. So there's a light ray that is along that direction. But because of the diverging lens, it's going to bend away. It's going to bend this light ray away from the symmetry axis. And for that particular light ray, it's going to emerge parallel. Okay, so this light ray, then there's the red one. So notice how if you're looking at this light, if you're standing over here and you're looking at the light that emerged from the lens, it looks like this light came from an image that's located right, so I'm going to trace this one back as well. See how all three of these things meet right here. So all of these light rays look like they came from that point right there. Now, the light, these light rays didn't actually come from that location. Notice how I had to trace the path of the light ray back in order to see that, oh, it looked like it came from there, but it didn't actually come from there. So for that reason, we call it a virtual image, because we had to trace the light ray back. And notice how this is upright. The arrow isn't upside down. And this is a reduced in size, reduced image. Okay, so those are our three principal rays for this example where we had a diverging lens. Now, if you only have a single lens, you might notice that a real image is always going to be inverted, and a virtual image is always going to be upright. Okay, and there are a couple other properties that you get used to when you play with this, or when you see all the cases. It turns out for a diverging lens, they all follow this. They're always like this. But for a converging lens, you can actually, if your object is within the focal length, you can actually have a virtual image. So you might want to play with that as practice. Try and have an arrow within the focal length and draw the ray diagram. Okay, so I want to say a few quantitative things here. Now, so I'm going to come back to magnification. In section 34.6, they lead up to these main equations. So I'm going to gloss over. You don't need to know this stuff. Like this formula right here, 34.20, you can skip it. All that I care about you knowing are these two equations. And really, the one that matters here is, or the most important one is the first one. That's the most important equation for this whole section on lenses. 1 over s plus 1 over s prime is equal to 1 over f. So this is called the lens equation. Okay. So in order to make sense of this equation, let's go back to a diagram and label what some of these quantities are. Right? So let's say we had a... so by the way, now is maybe the time that you could practice the, practice drawing a... suppose you had this example problem. You might want to pause it and try and draw the ray diagram right here. Okay, so pause it and try that right now. The answer is that, so you have one light ray, so you have a parallel one that goes towards the focus because we have a converging lens. And then we have another one that passes straight through the center there. So I drew this a little, so this is actually hard to see. I really need a ruler here. Let me try this a little better. So now I'm holding up, you can't see it, but I'm holding up a straight edge to my screen. This is harder than I thought on a tablet. There we go. So that's one light ray, and then another one is this one right here. So it's maybe hard to see, but see how these light rays are actually spreading out right there? So actually, if you trace these back, oh shoot. If you trace these light rays back, you'll get, and so the equivalent actually right here is, so there's one that goes through the focus on this side, and then that one emerges parallel. So actually all of these, if we trace them back, see how they're spreading out after they go through the lens? So if you trace all of these back, so by the way, the light is going this way for all of these. If you trace it back, it looks like you get a virtual image that's way over here. Right? Oof, that one's a tough one. If you did that one successfully, you're doing pretty well already. But really, these take a little bit of practice. Okay, so notice how we have a converging lens, but it's still a virtual, and this one happens to be enlarged because it's bigger. It's a bigger arrow. A virtual enlarged upright image. Okay, so I want to talk about the lens equation. So that was the original idea here. So so the convention for drawing these diagrams is that the object distance, which is s, is always positive. Okay, so in this formula, s is the object distance, and it's always positive. S is greater than 0. So this distance right here is s. F is a characteristic of the lens. It's the focal length. So remember, the magnitude is the distance that this is away from the lens. That's the magnitude of F right there. And then the sign tells you whether you have a converging or a diverging lens. So this is the focal length. So the focal length, and then it's positive if it's converging or negative if it's diverging. Now S prime is the hardest one of the three. And there's a sign convention that you have to follow for S prime. So S prime is the image distance. So the magnitude tells you how far away the image is from the lens. So the magnitude of S prime is going to be that distance right there. But there are rules for this. So this is the image distance. So this is the hardest part of this. And this is the part to keep in mind. So S is positive if the image is on the positive side, so on the right-hand side. The image is on the right. So I'm assuming here that S is starting from the left always. So in all of these pictures, notice how I'm always starting with the arrow on the object arrow on the left-hand side. So we're defining that to be the object side. Now, if the image is on the side opposite to the object, then S prime is positive. But if the image is on the same side as the object, then S prime is negative. If image is on the left. So S prime is negative if it's on the same side as the object. Okay. So for this problem, maybe we could estimate. So let's see how accurate our diagram was. So I'm just going to plug in numbers just to see how accurately we drew this. Okay, so it looks like maybe S was, what kind of triangle is that? Or what are the relative proportions here? Maybe it's 2/3 of the focal length. So let's check our diagram. Check diagram. It looks like roughly we had S is 2 centimeters and F was 3 centimeters. Does that look about right? S is 2, F equals 3. F is positive because it's converging, and the focal length is bigger in magnitude than the object distance. Okay, so let's go ahead and solve for S prime. So using our lens equation, we have 1 over S, 1 over 2 centimeters plus, and this is the thing we're solving for, we don't know what S prime is, equal to 1 over 3 centimeters. So 1/3 minus 1/2 is negative 1/6. And so S prime looks like it's negative 6 centimeters. So let's go back to our image and see if, so I didn't have enough room. So see how if this is 3 centimeters, our image should actually be farther to the left than where I drew it. But I didn't quite have enough space to show it on the tablet, so I kind of scrunched everything together. So the point is to be able to draw these ray diagrams accurately enough that when you double check the numbers using the lens equation, everything should match up. Notice how this is negative. And so the image is exactly on the negative side. So on the left, on the same side as the object. That's what that negative sign is telling us. Okay, so close enough. Could have drawn it more accurately though. Okay, there's a couple other things I want to talk about. But I don't want this video to get too long. So let's go back. So this problem is starting to seem pretty easy now. What kind of lens is inside the black box? Well, it took a parallel ray and it spread it away from the symmetry axis. So what kind of lens? This is a diverging lens. Is the image produced real or virtual? Well, it looks like the light rays that pass through the lens, looks like we have to trace them back in order for them to ever cross, in order for them to meet up. So it looks like we have we're going to have a virtual reduced. So see how if this light ray, the one that was initially parallel, if it spreads out and we trace it back and then see where it intersects with this line, it's going to be a smaller arrow. So it's a virtual reduced upright image. So all of that, just from those two light rays, we get all of that information. Okay, magnification. So this is what we skipped over from that previous section. So the magnification is m is minus s prime over s. So this tells you exactly how big the image arrow is relative to the object arrow. And the sign tells you whether your image is upright or reduced or inverted. Okay, so I would expect, so in this example right here, I would expect that the magnification is a number bigger than 1 and positive, right? Because it's upright and it looks like our image is bigger than our object. So let's double check. So in this example that we were doing in the black pen, so the magnification is minus s prime over s. So s prime was negative 6 centimeters. So I have to have two minus signs, one from the formula of magnification and one because s prime is negative. And then our image, our object distance was 2 centimeters. So it looks like our magnification is plus 3. So our arrow, if we drew everything correctly, it should be 3 times bigger than our object. And that's roughly true, 1, 2, 3. So I tried to squeeze it in there, but yeah, that's looks like it's about 3. Okay, one other thing. And that is this other formula that I said that you also need to know, this Lensmaker's equation. So what this is it tells us how to compute the focal length. So let me draw some pictures here. Lensmaker's equation. So let's suppose you had a lens that looked like this. Okay, so suppose it's flat on this side and it's curved on the other side. Right? So I already know that that's a converging lens, and I already know that f is positive for this one because it's thicker in the center than at the edges. Remember, that was what told us that it was a converging lens. So we can actually compute what the value of f is if we know a few things. So we need to know the index of refraction of the glass. So we need to know the value of n, making up the glass right there. So this equation, by the way, assumes that the surrounding air is, or the surroundings are air of n equals 1. So the n right here is whatever the lens is made of. So for the most part, it's glass, and n is somewhere around 1.5, 1.6, something like that. But you should be given that in a problem. Then the other things are the radii of curvature of the two sides. Now, ideally, to make a lens, you would use, like this shape right here would be a parabola, but it's not. It's much easier in practice to make spherical shaped lenses. It's much cheaper, much easier from the machinery. So the two sides have two different radii of curvature. So the one on the left is called surface 1, and then the one on the right is surface 2. And so each of these have their own circles. So this circle, this is the circle corresponding to surface 2. Right? See how I'm just continuing that. So for surface 2, I'm continuing that shape, that circular shape. And that has some, I'm going to scoot this over, and that has some radius of curvature. So from the very center outwards, that's some R2. So the magnitude of R2 is that. The only thing to keep in mind here is that there is a sign convention, and that's the hard part about using this formula. So the sign convention it's the same sign convention that we used for the S prime. So on the left, it's negative, and on the right, it's positive. So see how the center, so the second surface has its center on the left-hand side. So that's on the negative side. So R2 is negative for this example because it's on the left. So this is the same sign convention as for S prime. So R1 and R2 separately could be positive or negative. So it's up to you to determine. So what you do is for each surface, draw the circle. Is the center of the circle on the left-hand side or the right-hand side? So if it's on the left-hand side, then that radius of curvature is negative. If it's on the right-hand side, it's positive. Now surface 1 right here, if this is flat, then this is like a circle where it's infinitely big. So if this is flat, you can imagine it's part of a circle, but that circle has radius of curvature R1 equals plus infinity. It's on the positive side, so it's positive, but infinitely big in magnitude. So for this example, for the one I drew, well, let me write down so this is the general formula. So this is for any value of n, any R1 and any R2. And then for our example that we just drew, it looks like we could simplify this because we know R1 is infinitely big. So if R1 is infinity, because we have 1 over R1, that's going to be 0. So anytime you have a flat side that doesn't contribute, that contributes 0 when you take the reciprocal. And we have minus 1 over R2, but remember R2 is negative. So in our example, this is going to be minus a negative number. So this is going to be positive. So I'm just pointing out, so really I would plug in the numbers if we were given the radius of curvature of side 2. But I would make sure to plug in a negative number right there for R2, and with this extra minus sign that becomes positive. So n minus 1 is positive, and so when we solve for f, we get a positive number. And indeed, this will give us a positive f because it's a converging lens. Okay, so that was a lot of info. This was a relatively long video. So we'll definitely need to practice a lot of this in class. Okay.